Good afternoon, and welcome to this walkthrough of compound interest and borrowing questions. Compound interest, it's not a force of nature, it's a force of economics, but it's very much like a wave in that compound interest can either crush you or provide you an excellent surfing opportunity. If you'd like to be someone who's going to surf on the wave instead of be crushed by the wave, you need to know a little bit about waves. You need to be able to predict the ocean. You need to practice popping up on your board. And you might need to make some mistakes along the way too before you get a good ride. So consider today the beginning of that tutelage if this is new material for you. So in any case, our first question actually doesn't really connect with compound interest, but it does connect with applying percentages to numbers. So here we have the price of a car, $24,500, and we're going to add 13% sales tax. So in order to do that, we're going to create an expression that looks like this. 24,500. That's so small, so tiny. Mr. Jennings, it's such a tiny line. 24,500 multiplied by 0.13 is going to give us the amount of tax that we have to pay. This program is going to drive me nuts. I'm going to change programs. One moment. Okay, so we have here the price of the car, and we have two ways of doing this to apply sales tax. This is the long way. Multiply by 0.13 and then add the price of the car. Why do we do this? 0.13 is 13% as a decimal. And if we multiply the sales price by that, we'll get the tax. The total price will be the tax plus the original price. So that's this whole expression here, which is equal to, I'm not even going to work it out. This is the way I would do it. 24,500 multiplied by 1.13. This will give us the original price plus the tax price, all in one operation. So that's what I'm going to punch. 24,500 times 1.13 gives us 27,685. Is the price that we'll pay for the car. And then what's our next piece of information here? So we're going to make a down payment of 20% of the cost after tax and then finance the remaining. All right, so what does that look like? Determine the cost of the down payment. All right, so in order to find the cost of this down payment, I am going to do 27,685 multiplied by 0.2. This is 20% as a decimal. Why? Well, I take 20% and move this decimal once, twice to there, which will be 0.20, otherwise known as 0.2, otherwise known as 1/5. Okay, so all of these are the same. Now, this number will be equal to that times 2. So I'm just going to do this. I wrote it out on my calculator, multiply by 0.2, and that gives me 5,537. So I might write a therefore statement at this point. It would sound like this. Therefore, the down payment will be $5,537. So, okay, let's keep going. And then we want to think about what would be the benefits of making a larger down payment in this situation. Well, one of the drawbacks is you need to come up with more cash, and that's hard. But if you can, it means you have less to pay later. If you're paying less money later, you'll pay less interest, you'll pay less money overall, and you will ultimately save money in the long run. There's a lot of reasons why that might be good. Maybe you went with your friend to the car sales dealership, and they get to see you whap down a full 10 large on the counter, and it makes you feel good. I mean, there's lots of different potential benefits of doing a larger down payment in this situation. It really depends on you and your situation. Next, we learn a little bit about the 2010 rule. To be honest, I'm learning about the 2010 rule from this worksheet. Excluding housing debt, mortgage payments, and the like, you shouldn't be borrowing more than 20% of your annual net income. Okay, so what does that mean? Well, if I'm making $100,000 per year, K means thousand, So $100K per year. My debt that I maybe take on for renovations or to buy a car or something like that should be less than 20K. 20% of 100 is 20K. So I shouldn't be going into debt for much more than that, or else I might start to be strained by my debt. It's hard to buy that Tesla then, isn't it? You need to make a lot of money to buy that $200,000 Tesla. My goodness. So anyway, here we go. And excluding housing payments, mortgage payments, and the like, your debt payments month by month should not exceed 10% of your monthly take-home pay. Okay, so let's take a look at some examples. If you annually make $48,000, it's a maximum debt you would allow yourself according to the 2010 rule. Well, in this case, we're going to use this 20% because we want this maximum debt to be less than 20% of our income. 20% of 48,000, this is the way you would punch it on a calculator. 48,000 times 20%, 0.2, equals 9,600. So we would not want our debt to be greater than $9,600 based on this 2010 rule. If your monthly take-home pay, if you're taking home $6,300, so that's already someone who's doing better than that, because we know 12 times 6 is going to be bigger than 48. Anyway, 6,300, what's the maximum amount that you would allocate to monthly debt payments according to the 2010 rule? Well, according to this rule, we can do 10% of our monthly take-home. So in that case, it'd be $630. Just move the decimal place once. I don't know if your monthly take-home pay is $5,600. What's the maximum debt you would allow yourself according to the 2010 rule? Maximum debt has to do with 20% of your annual income. So if your monthly income is $56,000, this is what we need to do to find annual income. We would take $56,000, multiply it by 12 months in the year, and then I'm going to multiply by 20% because I want to say what's 20% of my annual income. So that will give me, doing it in my head here, 1,000. Oh, no, I don't want to do that in my head. 56,000 times 12 times 0.2. I guess I could have done. No, it's still annoying. 13,440. So 13,440 would be the maximum total debt that I would want to take on if I were that person who follows the 2010 rule. All right. Next, explain the difference between simple interest and compound interest. Here's one difference. Compound interest happens at banks. Simple interest tends to happen as a handshake between people and not mafiosos. If you borrow money from the wrong people, they will charge you compound interest. You can be sure they take every advantage they can. Compound interest favors the person that's lending money. Simple interest would favor the borrower. Okay, the reason being, with simple interest, well, actually, that's not necessarily true. If you're paying it down quickly, but your payment, anyway, let's not talk too much about that. The main difference here is that simple interest, the interest does not add on to itself. So if I'm in a situation where I borrow $100 at 10% simple interest, after 1 year, I'd owe 110. After 2 years, I'd owe 120. After 3 years, I'd owe 130. After 10 years, I would owe 200. 100 plus 10 times 10. Okay, so the interest never grows. It just stays constant, so it creates a line. Compound interest creates a curve, and this is because the interest grows itself. Okay, $1,000 is borrowed at a simple interest rate of 5% per year. Complete the table on the right. Okay, and then so here we go. Then I'm going to do simple interest down here, compound interest there. Okay, so, or I'll erase it, whatever, it doesn't matter. All right, so at 0 years, I would owe $1,000. After 1 year, I would owe $1,050. After 2 years, I would owe $1,100. After 3 years, it would be $1,150. After 4 years, it would be $1,200. And after 5 years, it'd be $1,250. $12,500. Sorry, $1,250, 1,250. Okay, so why did it do that? Well, first I take 5% per year, and I take 5% and I convert it to a decimal, which is 0.05. It is not 0.5. That would be 50%. That would be 1/2. This is 1/20th. This is 5%. Okay, so that's the number that I'm multiplying this by to find how much I'm adding. Or I can multiply by 1.05 to find the first one. But to be honest, use this one for simple interest. Find out that I'm adding 50 each time. 5% of 1,000 is 50, and I'm adding 50. Okay? I'm adding 50 every time. Now, is this relationship between time and total owed linear or nonlinear? It is absolutely linear because this is going up by a constant amount, 1. After every 1 year, I go up by 50. So that's a constant rate of change. And this is the line. Y is equal to 50 multiplied by the number of years that go by plus the initial amount, 1,000. That's the equation of that line. It's all linear. So we have a lot of tools to understand that. Too bad most financial math does not work that way. Most of it will work this way. 100,000 is borrowed with a compound interest rate of 5% per year. Let me see if I can set this up in Desmos to show you. Okay, we're back. So here I have a table, and in the first year, I know I'm going to have 1,000 that I'm going to owe. In the second year, I'm going to have 1,000 multiplied by 1.05. This is the formula that I would use. And then in the next year, I would have 1,000 multiplied by 1.05 raised to the power 2. Okay. I'm just going to copy this, and I'll fill in the formulas very quickly. To the power 3. Oops, that's not to the power of. To the power 3. To the power 4. And this one to the power 5. Okay, now zoom to fit. There we go. There they all are. So do these make a line? Well, they really do look linear, don't they? But in fact, they're not. If I take a look at this one, this is the point here, 1,000. And then the first year is the same as simple interest. We added 50. In the next year, we added 100 and then another $2.50. And then this one, we added another 50, but then like 5 something dollars extra there. And then here we had this is 4 years, $1,215. See, there's this little bit of extra that's growing there on top of everything that we've got there. And so what we have is this equation. Y is equal to the initial amount multiplied by 1.05 raised to the power x. See how it goes straight through all those? Still looks like a line, doesn't it? But if you can see the little bit of curviness, that's great. Let me zoom out and you'll see more curviness. See how curvy that is? If we zoom right out and we let that float at 50 years, 5% interest, you see it, that $1,000 does something crazy. It goes over $10,000 after 50 years. It's not crazy like credit card interest, but it is crazy. Here, this is credit card interest here. Way so much faster. That's credit card. Watch out for credit cards. Okay, let's keep going. So, no, that is not linear because I graphed it. It wasn't a line. It's growing by a different amount each time. By addition. By multiplication, it's growing by the same amount each time. Next, Daniel is planning to use a mortgage to purchase a house. Congratulations, Daniel. Most people do. Now, describe how each of the following affects the amount of interest he must pay. If the interest rate is higher, he will pay more interest. If the interest rate is lower, he will pay less interest. If he takes longer to pay that back, he will pay more interest. If he takes shorter to pay that back, he will pay less interest. If he has a larger down payment, the amount he finances will be less. He will pay less interest. If he uses a smaller down payment, the amount he finances will be more. He'll pay more interest. Okay, let's keep going. I could explain why, but maybe you understand why. And if you don't understand why those things are true based on the formulas or based on your mathematical intuition, come chat and we'll talk about why that is. Let's keep going, everyone. $2,500 is deposited into an account that pays simple interest at a rate of 3% per year. What will be the total amount in the account after 10 years? So let's put that together. 2,500, and then I'm going to multiply by 0.03%. This is the interest that's earned each year. Each year that will earn $75 of interest. We said 10 years, so it's going to be that much interest is earned. That's 10 years of interest. Then I'm going to add that to the initial amount. So there's going to be $3,250 in there after 10 years. $3,250. So how do I answer a question like this? Figure out how much interest is being earned a year. Multiply by the number of years, because this is simple interest. It does not compound on itself, and it just makes a line. So this is the line's equation is y is equal to 75x plus 2,500. Okay, and then I can just input values of x to find out how much is going to be in the account at that time. All right, how much interest will be earned after 10 years? We already found that out. It was 75 times 10, 750. Would doubling the interest rate in this situation also double the interest earned after 10 years? Well, yes. If we had 6% interest, we'd be earning $150 per period. And that's double the amount that we were earning. Yeah, so there you go. Anyway, let's keep going. All right. Now we've got this similar amount of money, but it's deposited in an account that pays compound interest. Hooray. I get to use all my new tools. It's only at a rate of 2% per year, though. Kind of a boring interest rate. What would be the total amount in the account after 10 years? Okay, so let's set up our formula. This is our formula here. The amount is going to be equal to the principal multiplied by 1 plus the interest rate raised to the power t time. I is the interest rate as a decimal. So first we're going to need to convert that interest rate to a decimal. And we know that interest rate is 2%. 2%. So 2% is equal to 0.02. Okay, so 1 plus that, so the amount that's going to be in the account is going to be equal to the principal, which is $1,200 right there, multiplied by 1.02 raised to the power 10 years. So let's evaluate. There it is, raised to the power 10. And then make a prediction before you push go. I predict that it's going to be grown by about a third. So it's going to be, thank you so much, about 1,600. Let's see. 1,460. Oh, my guess wasn't that bad, but it was a little optimistic. The amount that's in there is going to be equal to 1,460. I actually just had a conversation yesterday about some investments of mine that are exceeding expectations. It was very exciting. They're like $100 ahead of where they were supposed to be by this time after 6 years. Not very exciting, but still, it's better than the other direction. Anyway, let's keep going. Let's not get autobiographical. Okay, so how much interest will be earned after 10 years? Okay, well, what would the interest be earned if we started with 1,200 and now we've got 1,460? Oh, well, the difference would be interest. So there I'll just use a subtraction strategy. I will take $1,460 and subtract the amount I invested, and then that will give me $260 of interest. Would doubling the interest rate in this situation also double the interest earned after 10 years? No. Okay, and why not? Well, let's evaluate it and see. Okay, the only thing I need to do, I can use the same formula, but here I'm going to use 1.04, double the interest rate. And I will find that this probably is going to triple the amount of interest I earn. It's my guess. Let's see. So now I'm going to go clear, and I'm going to say 1,200, that's our principal, multiplied by 1.04 raised to the power 10 equals 1,776. So instead of earning $260 in interest, it earned $570. So it wasn't quite triple the interest, but it was more than double. Yes, it was more than double. A little bit more than double. like just a little bit more than double. So it's not like simple interest where doubling the interest rate just doubles what you earn. No, bigger interest rates do more than double over time because they compound on themselves. Okay, Franco wants to purchase this boat for 20 grand. The seller agrees to let Franco pay for the boat at a future date, but he charges compound interest at a rate of 4.5% per month on any amount not paid up front. Well, Franco should buy the boat next year. He should not take on this debt. This is terrifying. If he waits 5 months to pay off the balance, what if he waits a couple of years? Oh my goodness, this is terrifying. This is such a high interest rate. It's criminal. It's literally criminal. But anyway, but this is a handshake deal between two people, so there's not really laws that govern that. But good luck getting your money if you let this run for 5 years. How will a $3,000 down payment affect the amount of interest Franco pays? It will lower it because he's paying off some of this ahead of time. So he'll pay less interest overall. Okay. How would we use the answer from part A change if simple interest was used instead of compound interest? Well, it's still going to be less interest if it was simple interest, but this is compound interest. I don't know what to say. Let's take a look at this in a graph. Okay, so I'm going to put this into Desmos in just a moment because this is properly scary. All right, folks. So here is what he will owe. I took out the $3,000 down payment. So instead of paying $20,000, he needs to pay back $17,000 to get this boat right away. And then he pays 4.5% interest per month. So that's 4.5% as a decimal, 0.045. So it sounds pretty good. That's a low interest rate, right? 4.5%. No, it's per month. It's per month. So X is representing a number of months here. So I'm showing you only 5 years. Only 5 years of time, 60 months. Notice I've shown you all the way up to 100 grand, and his debt will pass 100 grand just after 40 months. Just after 3 years, the amount he owes will more than 5 times. It's a scary interest rate. Let's find out what he owes after 60 years. Okay, I'm just going to put in the line X equals 60, and then I find the intersection there. See, that's when X is 60. Then he will, after 5 years, he'll owe $238,000 to this person. So don't make handshake agreements with people at 4.5% compound interest per month on something like 17 grand. You need to save the money and you need to pay for it in cash. You cannot do interest like that in this lifetime unless you know something I don't. Maybe you do. You know your situation better than mine, but be careful. Okay. Now, each of the following expressions was used to calculate the end value of a one-time deposit that gained interest annually over several years. In each case, state the type of interest used, simple or compound. Okay. And the number of years. So let's analyze these. This one here looks like simple interest because this looks like the equation of a line. Okay. Here is the interest rate multiplied by the principal, which will tell me the interest earned over time per year. And then this would be the number of years, 15 at 4% interest, 4% interest, 15 years, borrowing or lending $3,500, simple interest. This one over here is using multiplication. And the clue there that it's simple interest is that we're using addition to add on more money each year. Here we're using multiplication. It looks like we've gone once, twice, 3 times to multiply by 2% growth. So this is 102% times 102% times 102%. So 3 years at 2%, and the amount invested was $400. Here, this is clearly compound interest because we have an exponent. Here we have an exponent, but they haven't written it as such. They've just written out 3 multiplications. But here they did us the favor of saying, multiply by this 20 times, please. That is 1.4% because after I move the decimal place once, twice, it's there. So that's 1.4% for 20 years, $30. Not the kind of thing that's going to shake anyone's socks. unless that's $30 billion, in which case it was probably a pretty darn good investment. All right, now over here, this one, or maybe it's not. I don't know how to invest billions of dollars. Okay, when you have $1 billion to invest, you're not getting advice from me. Okay, so get it from someone that has some experience with that. This one again, I see some addition, so pretty sure it's simple interest. This looks like 70 years, $12 invested at that time. Wait, no, it's not. $70 invested. So this is $70 at 12 years at 2.6%. There, that's how you would break those down and sort of understand what people are doing. Any questions, come find me. Simona, she's planning on to borrow $9,000 using a loan that charges compound interest at the rate of 2.3% per year. How much interest is charged for the fourth year of the loan? Okay, that's a tricky question. I am going to use my blank pages for that. So here is the $9,000 that she borrows. All right. We're interested in 2.3%, I believe. And we want to know how much interest was charged in the fourth year. So let's try that. So let's find out what it was in the third year and then what it was at the end of the fourth year. That way we'll know how much interest was charged. So I'm going to say 9,000 multiplied by 1.023 raised to the power 4. Where did I get these numbers, Mr. Jennings? 1.023 is equal to 1 plus 2.3% as a decimal. Okay? 4, this is how much money will be in total owed after 4 years. And then I want to know, well, what's the difference between that and what it was after 3 years? So I'm going to subtract the 3-year value, which is 9,000 times 1.023 to the power 3. And that is going to give me my answer. Let's work it out. Okay. 9,000 times 1.23. Yep. 1.023. My goodness. Delete. 0.23. That would make an enormous difference. Raised to the power 4 equals, so that's 9,857. 9,857 subtract this value. Notice I just rounded that to 0. So let's round it nearest dollar. It's fine. And then can I do this? No. 9,000 times 1.023 raised to the power 3 equals 9635.39. When I do the subtraction, I find out that it's about $222. $222. Cool. $222 or thereabouts. All right. It's equal to about 222. So notice that that's the amount of growth that happened between year 3 and year 4. That growth is the interest. So that's how you would do this type of problem. And then how much interest is charged for the 5th year? Okay, well, in order to do that, I can use the same strategy with the numbers 4 and 5 instead of the numbers 3 and 4. Okay, so here, I already know the 4th year, which is, so I'm going to have the 5th year, which is 9,000 times 1.023 raised to the power 5 minus the 4th year, which I already know is 9,857. Okay, so here, I can actually do this one and just multiply by 1.23 equals, undo, clear. All right, I'm just going to type it in. 9,000. Sorry, I forgot that 0, and that makes a big difference. Multiplied by 1.023 raised to the power 5 is equal to $10,000 now. And so then I subtract 9,857. $226. Wow, I paid more interest in the 5th year than in the 4th year by $4. Okay, so what's happening there? Are the answers in the same? Why or why not? Well, they're not the same because this is not a line. If we used a line, they'd be the same, but it's not a line, it's a curve. So the amount it changes over the length of this curve. So that's why it's different from one math perspective. Another math perspective would be the amount that I'm earning interest on or paying interest on has grown, so the amount of interest grows. If you were using simple interest, it would be the same amount of interest each year. It would not change. It would be a line. Changcha would like to deposit $1,000 into an account and leave it there until it has doubled in value as a result of interest. What compound interest rate would allow her to reach her goal in 20 years? Woo! All right, we have a bonus question here, folks. This question is for bonus marks. I know how to solve this question 6 ways from Sunday, but you don't. You may find that you need guess and check. You may use Desmos and use a graphing strategy. Okay. You could even use a graph paper strategy, although it would be tricky. With a logarithmic paper, you could do really well, though. Anyway, so what annual, and then there's also the rule of 72. So look up the rule of 72, and you could use that to solve this problem. Okay, so many different ways to do it. So try it. Try it all those different ways. Okay, and then show me your work, and I will give you up to 1% bonus for completing this question to a high level. Good luck, everyone, and best wishes with your review. And note that the answers are below. So if you want the bonus points for this question number 12, you definitely need to show me your work and explain it to me and understand it. It's not enough to have a tutor show it to you and then not be able to explain it to me. You need to understand how to do this type of question. And that'll serve you very well for grade 11 because you'll answer these types of questions in grade 11 with a variety of methods. Yeah. And then let's see. Loans are often paid using a series of payments made at regular intervals, annually, monthly, biweekly. The type of payment schedule is called an annuity. Predict how the payment frequency would affect the total interest paid. Use an online loan calculator to check your prediction. We're going to do stuff like this tomorrow. So play around with it today and you'll be well prepared. Okay. And bye for now, everyone. I hope your math practice was fruitful. I hope you feel a little bit ready to surf this wave. Look at that cool wave there, eh? It's like this wave of money that's going to either bury you or surf you towards retirement. So you definitely want to be on the right side of this wave. And I do believe your knowledge that you can develop now and refine in grade 11 and continue refining into your master's program in finance, it's all going to help. All right. So best wishes. I hope your math practice is fruitful. Any questions, hit me up by email. Bye.